This meeting is being recorded.
In the next section of Chapter 16, we're going to review molecular orbital theory and see how it applies to this section specifically. When we look at atomic orbitals, so we have atomic orbital theory, when we combine our p orbitals, like so, we can create two new molecular orbitals. So if you recall, the number of atomic orbitals in would equal the number of molecular orbitals that are produced. So we see that instead of an orbital only applying to an atom in atomic orbital theory, in molecular orbital theory, these electrons extend over, or the orbitals extend over the whole molecule. So the movement of electrons also. So these overlap of p orbitals in ethylene, if we were specifically looking at ethylene, the 2p orbital, each electron here would overlap to form a bond, and we produce our lower energy pi bonding molecular orbital with these two two 2p electrons that are overlapping. And then we also create our second molecular orbital, will be the higher energy up here with this node present. This would be our pi antibonding molecular orbital. So 2p electrons in to produce, or 2p atomic orbitals in to produce these two pi bonding and antibonding molecular orbitals. So if we were to look at butadiene here and describe it in terms of molecular orbital theory, we have butadiene sketched out here in this pink structure, and then the four p orbitals drawn in, overlapping each of the carbon atoms involved. And that's what we see over here, those four p orbitals from butadiene that are involved in these two double bonds that are formed. And we see our drawn out notation here in this middle section, where we have our lowest energy molecular orbital shown here as orbital 1, where we have that overlap of these pi electrons. Then we have a higher energy here orbital with one node. And then like so, as we get higher and higher in energy in these four molecular orbitals, we see that we have up to 3 nodes present here. So the message here is that these 4 pi electrons in butadiene, they will occupy the lowest energy molecular orbital possible. So what we see here is that we have our first 2 pi electrons in this first molecular orbital, and then we have another 2 shown here. So in, again, the lowest energy molecular orbital, we see this constructive overlap at carbon 2 and carbon 3. Right, so we see this phase overlaps and this phase overlaps, and that's what we see here. So again, this is just a shorthand notation of what we see over here. So the length of a carbon-carbon central bond in our butadiene, we might have seen an explanation using atomic orbital theory and hybridization in an earlier section, but now molecular orbital theory can offer us a different explanation, in the sense that since these phases constructively overlap at carbon 2 and 3 here, so in the middle, we see that this actually displays a double bond character because of that overlap seen. So that can explain, instead of the hybridization being sp2 versus sp3, as we saw previously, this is now saying that this bond actually has a double bond character, and that's what makes it shorter. So we can see another example here of 1,3,5 hexatriene drawn out going from our atomic orbitals here. We have our 6p orbitals, giving us those three double bonds present in this compound. And we see our molecular orbitals filled down here at the lower energy, the first three molecular orbitals having 0, 1, or 2 nodes, and these upper higher energy molecular orbitals would remain unfilled for this compound here. So reactions that molecules undergo can often be or explained or elaborated based on what are called their frontier orbitals. So we can identify two orbitals of interest, which would be called these frontier orbitals, the HOMO, or the highest occupied molecular orbital, or the LUMO, the lowest unoccupied molecular orbital. So we can use light, for example. So commonly you'll see like H nu here. And light can promote or give enough energy to an electron to promote it to a higher molecular orbital, a higher energy molecular orbital. So that's what we see. This electron is being promoted here from orbital 3 to orbital 4. And we have changed our the highest occupied molecular orbital to now be 4 in the excited state after that light energy was used to excite that electron. So these are collectively then referred to as the frontier orbitals, these the HOMO or the LUMO orbitals. So that is everything that we will introduce in this section, and we will take a look at 16.4 in the next video.